Okay, let's now talk about another concept called drag forces. Now, drag force is a kind of frictional force. When I drop this eraser in air, as the eraser keeps falling, it is falling through air. That means it has to overcome a resistance. It has to push away the air to go through it. That is a drag force. When you want to swim in water, isn't it difficult for you to swim? Why? Because you need to take the water apart and go and occupy the space water has been occupying. You need to overcome a resistance. Well, the resistance becomes very obvious if you drop a piece of paper. Is that right? When you drop a piece of paper, it takes a long time to fall. Have you ever tried that? Now, when I allow this paper to fall, well, you can actually see it takes a little while to fall. There you are. Now, why does it take that long? On the other hand, this eraser falls pretty fast. Well, there is a drag force preventing the paper from falling. Now, what does the drag force actually depend on? As an object keeps falling, its speed increases. As the speed increases, the drag force also will increase. So, in many cases, drag force depends on the speed. Now, if you take a can of engine oil and put it in a transparent container and you drop an iron ball into it, it is very interesting to watch it. As it keeps falling, it will reach a uniform velocity. It will stop accelerating. As it keeps falling, its velocity increases, and as the velocity increases, the drag force also increases. As a result, after some time, the weight of the ball acting downward will be balanced by the drag force. And from that time on, there will be no net force on that object. Well, when an object moves in a medium such as air or water, it experiences a drag force opposite to the direction of motion, which reduces its speed. The drag force increases with the speed of the object. You know, when you swim slowly, the resistance is not as much as when you want to swim fast. The speed increases, the resistance also increases. Now, consider an object falling freely. Now, what are the forces acting on it? Its weight mg is acting vertically down, and the drag force will be acting vertically up. As the velocity of the object increases, what happens as the velocity of the fall increases, the drag force will also increase. Until a time will come when the weight is equal to the drag force. Now, at this stage, there will be no net force acting on the object. So, if you jump from a very big height, as you keep increasing your speed, the resistance of fall will also increase. A time will come when your weight acting downward will be exactly equal to the drag force, and at that time there is no net force on you. That means there will be no more acceleration. You will keep falling with the same speed. You see that? It's a very interesting phenomenon. Now, from this time on, the object will fall with a constant velocity, and this constant velocity is called the terminal velocity. Now, some objects, you see, This paper takes a very long time because the paper reaches the terminal velocity very fast. You can see it falls almost with the uniform speed, whereas the eraser takes a long time to reach the terminal speed. If you want this to reach the terminal speed, you need to drop it from a big height. Well, have you ever gone on skydiving? You can experience that terminal speed if you go skydiving. Now, here is the illustration of somebody skydiving. Now, the moment you jump out, there is only one force on you. You see? At the time you jump out, there is only one force on you, and that is your weight. Now, suppose this man has a weight of 100 Newton. He's a fairly heavy man. Now, with time, he will increase his speed. As the speed increases, the drag force will increase. So, soon the drag force becomes, say, 400 Newton. What is the net force on him now? The net force is only 600 Newton. That means he's not falling as fast as he did first. Because the net force is now small, the acceleration is small. But he is still increasing his speed. Because he is increasing his speed, the drag force will now increase. Now, a time will come when the drag force and the weight are exactly equal. The weight is 1000 Newton, the drag force also is 1000 Newton. The forces on the skydiver are now balanced. That means from that time on, the skydiver will be falling with a uniform speed, and that is his terminal speed. Any object that is dropped from a sufficiently great height will eventually achieve terminal speed. Let's do a small problem. A skydiver of mass 60 kilogram can slow herself to a constant speed of 90 km per hour by adjusting her form. What is the magnitude of the upward drag force on the skydiver? Well, at the time the skydiver achieves that uniform speed, uniform constant speed, her weight is balanced by the upward drag force. That is the one we use to do that problem. Alright, let's do that. Now here's the skydiver. Well, I got a poor picture for her, but I think you will excuse me for that. The diver is falling with a terminal speed of 90 km per hour. Now, there is no net force on the diver at that time. When the speed is the terminal speed, there is no net force. That means the weight acting on her, what is her weight? Mass times acceleration due to gravity, that is 588 Newton is acting vertically down. And the drag force will therefore be acting up and exactly equal to 588 Newton. Therefore, the upward drag force on her will be 588 Newton. There you are. Alright, now the second part is if the drag force is equal to bv squared. What does that mean? In this case, the drag force is proportional to the square of the velocity. That means as the velocity increases, the drag force will increase not linearly, but according to the square of the velocity. So we should be now able to say this drag force, which drag force? This 588 Newton equal to bv squared, where v is that terminal speed and b is the constant of proportionality, and we are required to find that's the value of that. So v equal to 90 km per hour, that is 25 meter per second. Therefore, we can say 588 Newton equal to B times V squared, 25 meter per second squared, or B equal to 588 divided by V squared, that is 0.94 kilogram per meter, and that is the value of B. Okay, another problem, a similar one. A small pollution particle settles towards the earth. What is a pollution particle? Now, if you look, most of us say, oh, our living room, our house is so clean, there is no dust in our room. But if there is a light coming into your room through a hole, look into the path of that light in your living room. There will be so many dust particles. You see, dust is roaming around all over. In fact, when I look at the light of the projector, I can see a lot of dust particles there. That's a pollution particle. And that pollution particle, very often, because it is so small, they will reach terminal speed very fast. So as it moves down with the terminal speed. That's what this problem is talking about. A small pollution particle settles towards the earth in still air with a terminal speed of 0.3 millimeter per second, very slowly. The drag force on the particle is 10 to the power of, the mass of that particle is 10 to the power of negative 10 gram. And the retarding force is of the form B times V. Retarding force is of the form B times V, means retarding force or the drag force equal to BV. What is the value of B? The same problem that we did before. We can find the drag force. We first find the drag force. How do we find the drag force? Because the pollution particle is moving with the terminal speed, the drag force opposing motion equal to the weight of the pollution particle. Well, we know the mass of the particle, therefore we can find its weight. Mass is 10 to the power of negative 10 gram. You need to convert that to kilogram. 10 to the power of negative 13 kilogram. The terminal velocity V sub t is 0.3 meter per second. Is that 0.3 meter per second? No, 0.3 millimeter per second. I meant to write millimeter here and convert that to meter. That will be 3 times 10 to the negative 4 meter per second. This is 0.3 millimeter per second, which is 3 times 10 to the negative 4 meter per second. Now, can you see the pollution particle I have just drawn here? The weight is 9.8 times 10 to the negative 13 Newton. And when it is in terminal speed, the drag force will be acting upward and will be exactly equal to the weight. And we are told that the drag force is of the form BV. So mg, the weight of the pollution particle, is the same as the drag force BV. So solving for V gives you B equal to mg over V sub t. M is this, and V is given to us, which is, yes, this one, 3 times 10 to the negative 4. So mg, 10 to the negative 13 times 9.8 over 3 times 10 to the negative 4, and that is 3.3 times 10 to the negative 9 kilogram per second.